It's now time to discuss section 5.5, which is u-substitution integration. We learned with the fundamental theorem of calculus how to integrate the definite integral by taking the antiderivative function at the upper limit of integration and subtracting the antiderivative function at the lower limit of integration. However, this requires us to have an antiderivative function. And finding an antiderivative function is not always easy. Remember that for integrals, we only have basically three rules. The integral of a sum is the sum of the integrals. The integral of a difference is the difference of the integrals. And the integral of a constant times a function is the constant times the integral of the function. There's no one rule that deals with products in the integrand or quotients in the integrand. Instead, we learn a lot of different techniques to tackle different types of these types of integrands. In this video, we're going to learn the first such technique, which is u-substitution integration. We'll spend a lot of time in calculus too, learning some other methods. U-substitution integration is what I would call a bread and butter technique. It is very basic and gets used a lot, as in tremendously often. This is one that you need to master at the 95% level or above. You've got to be good at u-substitution integration to continue into Calculus 2 and Calculus 3. Where does this u-substitution integration come from? Well, remember that when we took derivatives of a composition, a composed function, f of g of x, we took the derivative of the outside function, left the inside alone, and then multiplied by the derivative of the inside function. In other words, the derivative of f of g of x was f prime of g of x times g prime of x. Now we're going to look at integrands that basically are the result of some chain rule derivative, and we're going to learn how to undo them. We really only have two learning objectives in this section. One is to learn how to do the chain rule undo, u-substitution, on an indefinite integral, and then to learn to do u-substitution on a definite integral. Let me share my screen so we can get started. So how can we recognize that we need to use u-substitution? In general, what we look for in the integrand is a composed function. Since the derivative of a composed function gives us the derivative of the outside, with the inside still composed inside of it, and then multiplied by the derivative of the inside. So what we're typically looking for is some f of g of x multiplied by the derivative of the inside function, or f of g of x times g prime of x. Now, we may not get exactly g prime of x, but we need to have it up to a constant. If we don't have the constant, we can deal with that by multiplying by a form of 1 that gives us the correct constant, or by simply solving for the differential, and the constant will work its way through. In other words, if g turns out to be something like x cubed, so that I have 3x squared as the derivative, I can still integrate using u-substitution as long as I have x squared as a factor inside the integrand. I don't necessarily need the 3. I can deal with the constant. So what we're looking for, again, is composition in the integrand. We're going to call this u-substitution because we're going to substitute part of the integrand with the variable u, and another part of the integrand with the derivative of u, du, the differential. We're also going to use what's called an abusive notation in order to isolate the differential du about the dx. This is also sometimes referred to as a change of variables because you're changing the integral from being an integral with respect to x to an integral with respect to u. This means that the differential must also change from dx to du. We are literally changing the variable inside the integral. If it is an indefinite integral, when we have completed the integration, we have to back substitute to get back to the original variable, say x. If it's a definite integral, we're looking for the net area between the curve and the independent axis. We will instead stick with u, use u limits of integration, and complete the problem without ever returning back to the original variable. It can be done by returning to the original variable. It's more work and tends to lead to more careless mistakes. Note that if it is a definite integral, we have to change the integrand to being in terms of u, the differential from dx to du, and the limits of integration from x values to u values. Let's start with the indefinite integral. We're going to suppose that we have a function g, and we're going to let g be u. We want the derivative of g to be continuous over some interval, let's say from a to b. Then we want another function, which we're going to call f, and we want f to be continuous at the corresponding range of g. In other words, the derivative of g is continuous on a to b. And if I take a to b and put it into g, I get out y values. Those y values are going to go into the function f because f is composed with g. So I need the outside function f to be continuous at the corresponding range of g. Then we're going to take an antiderivative function of the outside function. We'll call uppercase f the antiderivative of lowercase. What we're trying to undo is an integrand where we have composed f with g and multiplied by the derivative of g. We need g prime to be continuous over the interval, and we need f to be continuous over the range of values that g produces using the same x values that g prime is continuous on. If this is the case, then I can substitute u in place of g of x, and I can substitute du in place of g prime of x dx. This gives me the outside function lowercase f at u integrated with respect to the variable u. This gives me the antiderivative function uppercase f of u up to the constant of integration. And then, because it is an indefinite integral, I have to return to the original independent variable, which is x. So I back substitute and replace the u back with the inside function, g of x. Let's take a look at the proof of this theorem. We start with our conditions that we have a function g of x and we set it to u, where the derivative of g of x is continuous over some interval, say from a to b. And then if we take the interval a to b and we put it into g, we get out a range of y values. Those y values are put into f as the domain values. So f needs to be continuous on the corresponding range of g. We also have an antiderivative function for the outside function lowercase f. All of those are the conditions. Those are assumed to be true. What we're trying to prove now is that the integral of f of g of x times g prime of x dx gives us the antiderivative function with g of x substituted inside. We start with more or less the definition of the antiderivative function with g of x substituted inside, and we take the derivative of it. We know that uppercase f is the antiderivative of lowercase. However, it is itself a function and it's composed with g. To take the derivative of it, we apply the chain rule. This gives us the derivative of the antiderivative, freeze the inside at g of x, and multiply by the derivative of the inside, g prime of x. However, we know that the derivative of the antiderivative is the function lowercase f. So we can replace this with lowercase f of g of x times g prime of x. Now what we do is we're going to integrate both sides of this equation. We add an integral symbol on the left with the differential dx, and we add the integral symbol on the right with the differential dx, since that's the independent variable. Now, the integral of a derivative is simply going to, well, they undo each other. So you get back the integrand unchanged up to a constant of integration. So this left side becomes the antiderivative of g of x plus the constant of integration. This must be equal to the integral of lowercase f of g of x times g prime of x. Remember that f and g are composed. You're taking a function and substituting it inside of another in place of the variable. That's not multiplication. Once we have this, we're going to go ahead and substitute u for g of x and du for g prime of x dx in this equation. This gives us lowercase f of u du, which we know we can integrate with respect to u. When we integrate with respect to u, we get the antiderivative function uppercase f of u plus the constant of integration. Then we can back substitute that u is equal to g of x, and we have completed the proof that integrating a composed function times the derivative of the inside gets us the antiderivative of the outside function with the inside function substituted plus the constant of integration. When we're applying this process, we need to look for a composed function inside the integrand and a multiple of the derivative of the inside function multiplied by that composition. They must be multiplied in order for this to be an application of u-substitution integration. Now, what we want to do is set up basically a problem-solving strategy. So let's go through some of these steps. In order to decide if you need u-substitution, you need to look at the integrand and you need to determine if you have composition. If you have composition, look at the inside function. Compute in your head what the derivative of it is. Look to see if you have a multiple of that factor multiplied by the composition. If you do, this is u-substitution. Once we've identified that, we're going to identify the outside function as lowercase f and the inside function of the composition as g of x. Let the inside function be u. Make sure that when you do this, that whatever inside function you choose to be u, you do have its derivative, except for maybe the constant, in the integrand as a factor. Then we're going to take the derivative of both sides. We're going to compute the derivative of u with respect to x, which of course is the derivative of g with respect to x, or g prime. Then we complete what's called an abuse of notation. Yes, that's really what we call it. We split apart the differential notation du dx. We know this shouldn't be possible because That's an operation that represents the derivative. It is not, in fact, a fraction. The genius of Leibniz's notation is it always works, and so we do it. So we're going to take the denominator differential and swing it around to the right side to isolate the differential du. Du then becomes g prime of x dx. Once we have this expression, then we'll be able to substitute in the original integral. Sometimes, for some students, it's simpler if instead of solving for g of du, they instead go ahead and after isolating the du, they then solve for just the differential dx. And then they can substitute for dx in the original integral. The next step is to complete the substitution. Place g of x with the variable u and either replace g prime of x dx with du or dx with du divided by g prime of x. Both methods work always, so you can choose the one that feels the most comfortable for you. Once you've substituted, keep in mind that if you did not have the correct constant for g prime, that you will actually be substituting the derivative du divided by that constant equal to g prime dx because you didn't have the constant. This will all come out sort of in the wash. You don't have to worry over much about the constant showing up. The algebra will take care of it. At this point, you should have converted everything in the integrand and the differential to something in terms of du. And now you can integrate with respect to u. If the integral cannot be evaluated, then it either was not a u-substitution problem or you made a poor choice for u. Go back and try to pick a different inside function. If it is a definite integral, we will compute new limits of integration. Instead of being x equals 0 to x equal 2, say, have to change it to u equal the number corresponding to x equals 0 and u equal a different number corresponding to x equal 2. We'll use our definition for u equal to the inside function to find the right value of u for the corresponding values of x. Then we evaluate the integral. If it is a definite integral, we'll get a constant value and we'll never need to return to the original independent variable. If it's an indefinite integral, then we will need to return to the original independent variable and back substitute out of u and back to x. Don't forget to do that most important step on an indefinite integral. Now that we've talked about the problem-solving steps, let's go through a couple of examples together. This is such an important method and becomes such a key part of how you integrate so many problems in the future that you really do have to master it at a very high level. If I had to choose one skill for you to have moving forward into Calculus 2, it would be u-substitution. Let's take a look at example 1, which is the integral of sine to the 10th of theta cosine theta d theta. This is an indefinite integral, and the independent variable is theta. When I'm done, I need a function of theta up to the constant of integration. First, there are a couple of ways of proceeding, so I've kind of split them into two. Note that the sine function is composed with the power function x to the 10th. In this case, we can take sine to the 10th of theta, and we can rewrite it instead as the sine of theta raised to the 10th power. That means the inside function is evaluated first, sine of theta, and then we raise it to the 10th power. Because sine theta is on the inside, it becomes our g of x, or our u. And the thing on the outside is basically x to the 10th or theta to the 10th, and it becomes our outside function, f. Now, what we want to do is set our u to be the inside function. In this case, our u is going to be sine theta. In order to feel more confident that this is probably the right way to go, in your head, compute what the derivative of sine theta is with respect to the original differential d theta. The derivative of sine theta with respect to theta is cosine theta. Look in the integrand to see if you have a multiple of cosine theta as a factor. And indeed, we do. This should give you confidence that you're using the right technique. To find du, we simply apply the derivative with respect to theta, the original differential, on both sides of our definition of u, highlighted in yellow here. The derivative of u with respect to theta then becomes cosine of theta. And next we apply this abusive notation, which shouldn't be allowed, but because it works, we do it. This is the genius of Leibniz's notation, why we're still using it some 330 years later. We swing the d theta around to the right-hand side so we can isolate the differential du. At this point, there are two ways that you can go. You can isolate d theta, since that's what's in the original integral, and substitute for it. Or you can recognize that cosine theta d theta is also in the original integral, and you can substitute du in place of that. You have to make a choice, and it just depends on how your brain works, what occurs to you on that problem. What we're going to do in method 1 is we're simply going to substitute u for sine of theta, and we're going to replace cosine theta d theta, g prime dx, or g prime theta d theta, with du. Notice that I rewrote the form of the integrand from sine to the 10th of theta to sine of theta to the 10th to make it more obvious what the inside and outside function are. I replaced sine of theta with u to get u to the 10th. I replaced cosine theta d theta, derivative of the inside function times the original differential, with du. This gives me an indefinite integral in terms of u and u only, which means I can integrate using the normal rules: sum and difference rule, the constant rule, and the power rule for integrals. I add 1 to the power to get 11, divide by the new power, and add the constant of integration. However, the original integral is an indefinite integral in terms of theta. In order to complete this problem, we have to return to the original variable, which is theta. In order to do that, we simply back substitute, and we replace u with sine of theta. And again, you could either write this as sine to the 11th of theta divided by 11 plus the constant of integration, or sine of theta in parentheses raised to the 11th power, all divided by 11 plus c. In method 2, I want to show you what it would look like if instead you solve for the original differential d theta. Remember that when we were solving this problem, we reached a certain point where we had du d theta equal to cosine of theta. Next, we abused the notation and we swung the d theta around to the right-hand side. Another technique that is very frequently used is to solve for the original differential by dividing both sides by any factor attached to it. This gives us that d theta is du divided by the cosine of theta. Now when I substitute, I'll be substituting sine of theta for u, and I'll be substituting du divided by cosine of theta for d theta. won't have anything to substitute for the cosine of theta, but notice that they cancel once I've made my substitution for d theta. It results in exactly the same indefinite integral, which gives us the same function, and we back substitute finally to get back to our original variable theta. Now I want to take a look at a problem where a multiple of g prime of x appears in the integrand, but not exactly g prime as in the previous example. Let's take a look at example 2 now. In example 2, we have the integral of x times e to the 3x squared plus 1 power dx. This is also an indefinite integral, and the independent variable is x. So we are going to have to return to get a function in terms of x plus the constant of integration at the end. In order to determine whether it's u-substitution, look for a composed function. In this case, I have the polynomial 3x squared plus 1 inside the power of the exponential e to the x. Polynomial would be done first, then when I get a number, I would put it into the exponential. That makes the exponential the outside function, and the polynomial 3x squared plus 1 the inside function. Now, when I think about the 3x squared plus 1, I want to take the derivative of it with respect to the original differential dx. I take the derivative, I get 6x. I should have a multiple of 6x as a factor in the integrand if this is to be u-substitution. I don't have 6x. I have x, which is a multiple of 6x. It would be 1/6 of 6x. As long as I have the x, I can use u-substitution. When I'm looking at this, then, I will be able to replace the 3x squared plus 1 with u, and the x will become a part of the du. It is a part of the g prime of x dx. Let's now go ahead and look at a couple of different ways to proceed. It is possible to multiply by a form of 1, 6 divided by 6, to get the 6x you need. But again, it's not necessary to do that. The constant will work its way through algebraically. We choose u to be the polynomial, and to find du, we take the derivative of u with respect to the original differential dx. This gives us du dx equal to 6x. And then we abuse the notation and swing the dx around. At this point, you have to make a choice. There are two ways to proceed. You can either, once you have swung the differential around so that you have du equal to 6x dx, you can either solve for x dx, which you do have in the original integrand, by dividing both sides by 6, or you can simply solve for the original differential dx, and the rest will take care of itself. It's totally up to you. Either solve for x dx, here's the original integral, gives you du divided by 6, or solve for the original differential, which gives you du divided by 6x. In this particular problem, when you substitute for them, you are going to end up with e to the u power times du divided by 6. I said the constant will algebraically take care of itself. Now, the 1/6 is a constant in the integrand, so we can factor it out of the indefinite integral and pull it to the front. Once we pull it to the front, we have the integral of e to the u with respect to u, which can be integrated. The antiderivative of e to the u is e to the u. And we end up with 1/6 e to the u plus the constant of integration. However, it was an indefinite integral in terms of x, so we have to back substitute. Our u was 3x squared plus 1, so in the final result, we replace u with 3x squared plus 1. Let's talk about good places to find u. This is very similar to what you were doing when you learned to apply the chain rule. So you're going to look for the same places. Powers of exponential functions, as in the previous problem. The base of something raised to a constant power, as in the first problem. Sine of theta was raised to the 10th power. It could be the argument to a trig function, or the argument to a natural log function. There are occasions when it turns out to be the denominator of a fraction. These are all good places to find u. You could also say take the radicand, the part underneath a radical, and let that be your u. There are all different ways to find and work with u. Remember that when you're abusing the notation by swinging the dx around to the other side, you're trying to build that g prime of x dx, or a multiple of it. And you can either try to get the factor that's in the original integrand exactly, or you can solve for dx and substitute, and it'll work both ways. Let's go ahead and take a look now at example 3. In example 3, we have the indefinite integral of 3x squared times the quantity x cubed minus 3 raised to the 2nd power. I can see right away that I have composition between x cubed minus 3 on the inside and something raised to the 2nd power on the outside. And I look for the derivative of the inside, or at least a multiple of it, inside the integrand as a factor, something multiplied by the rest of it. The derivative of x cubed minus 3 is 3x squared, and I have exactly that inside the integrand. This makes this a u-substitution, with the inside function being x cubed minus 3 and the outside function being the 2nd power. Let's go ahead and set this problem up now so we can work it. Let's go ahead and write down that the inside function, which is g of x, is going to be x cubed minus 3. And the outside function is going to be the power. This is the f of x. In this case, x squared. This means that I let u equal the inside, x cubed minus 3. Next, I take the derivative of the inside with respect to the original differential. So I compute the derivative of u with respect to x, which gives me the derivative of x cubed minus 3, which becomes 3x squared. Next, after taking the derivative of u, I want to abuse the notation and swing the dx around to the other side. This gives me du equal to 3x squared dx. Now at this point, you have a choice. You can go either way. If you choose, you can leave this as du equal to 3x squared dx, since you have exactly that inside the original integral in the highlighted part here. And that means that you can replace it with the du. Let's now take a look at what that would look like. When you do your substitution, you'll have the integral 3x squared times x cubed minus 3 quantity squared dx. And when you substitute, you're going to have u squared du. In other words, you replaced the inside function, x cubed minus 3, with u, and it became squared, the outside function. And you replaced all of the rest of the integrand, the factor 3x squared and the differential dx with the du. Let's take a look at what it would have looked like if instead you had solved for dx. Solve for dx, you'll have du divided by 3x squared. This time, when you substitute, you will instead not have anything to substitute for the 3x squared, but you can still replace the x cubed minus 3 with u and replace the dx with du divided by 3x squared. Then the 3x squareds cancel, and you end up with exactly the same indefinite integral u squared du. Once you've reached this point, you're ready to integrate, but with respect to u, not x. This is a polynomial, so we can use the power rule for integrals. Add 1 to the power and divide by the new power. This gives me u cubed over 3 up to the constant of integration. Now again, this is an indefinite integral, so I have to return to the original independent variable, which is x. Go back up and find your substitution equation. Your substitution equation is the one where you set what u was. U is x cubed minus 3. Come back down and make the substitution for u. I'm going to move the 1/3 to the front, and I'm going to replace u with x cubed minus 3 to the 3rd power plus the constant of integration. This will be your solution. Let's now turn our attention to example 4. In example 4, we can see that we do have a composition. We have x cubed plus 5 being raised to the 9th power. Again, in order for it to be u-substitution, I need a multiple of the derivative of the inside as a factor in the integrand. The derivative of x cubed plus 5 is 3x squared. I have an x squared, but not the 3. Since the 3 is a constant, I can deal with that. I can't put in a variable, but I can put in a constant. Go ahead and pause the video now, work this one out, and then turn the video back on so we can compare our results. So let's compare our results. The inside function is x cubed plus 5. The outside function is x to the 9th. We set u to be the inside function. Then we take the derivative with respect to the original differential dx. This gives us 3x squared. We abuse the notation to solve for du as 3x squared dx. Then we have a choice. We can either solve for the remaining factors in the integrand, the x squared dx, which would give us du divided by 3, or we can solve for the original differential, which is dx, which gives us du over 3x squared. Both methods work. They'll always work. Choose the one that makes the most sense to you. If you chose to solve for the remaining factors in the integrand, the x squared dx, you're going to replace the inside function with u, giving you u to the 9th, and you will replace the x squared dx with 1/3 du. Then you integrate with respect to u, which gives you 1/30th u to the 10th plus c. Finally, because it's an indefinite integral, you back substitute to get the final answer in terms of x. If you chose to solve for the original differential, you'll replace the inside function with u, the original differential with du over 3x squared. You won't have anything to substitute for the x squared factor in the integrand. However, it will cancel with the x squared inside of the definition of dx, and you end up with exactly the same indefinite integral in terms of u. Let's take a look now at example 5. In example 5, we again have composition of functions. I have a polynomial 2x plus 5. That is the argument to a cosine function. That makes 2x plus 5 the inside function, cosine the outside. The derivative of 2x plus 5 is simply the constant 2. But constants aren't something we have to worry about with u-substitution. Go ahead and pause the video to work this one out on your own. Once we set u to be the inside function, we take the derivative with respect to the original differential. This gives us the constant 2. And we abuse the notation to swing the differential dx to the opposite side. In this problem, whether you're solving for the differential dx or trying to get what's left in the integrand, you're doing the same thing, isolating the differential dx, which gives us du divided by 2. Next, we're going to substitute these things into the original integrand. We replace 2x plus 5 with u and the original differential dx with du over 2. The 1 over 2 is a constant factor pulled to the front. When I integrate cosine of u with respect to u, I get sine of u. And since it's an indefinite integral, I back substitute and write the solution in terms of the original variable x. This gives me 1/2 sine of the quantity 2x plus 5 plus c. Let's now take a look at example 6. Example 6 is one more similar to one of the examples we worked earlier. Pause the video to work this one out, then turn the video back on so we can compare our results. In example 6, we have the indefinite integral of x times e to the x squared power dx. In this case, the inside function is the power on the exponential x squared. The outside function is e to a power, or e to the x. We set u to be x squared, take the derivative with respect to the original differential dx, which gives us 2x. We abuse the notation and swing the differential dx to the right, solving for du as 2x dx. Now you have a choice. You can either solve for the remaining factors of the integrand other than the composition, or you can solve for the original differential dx. I chose to isolate the remaining factors, x dx. This gives me du divided by 2. Now I go ahead and I substitute u for x squared and du over 2 for x dx. This gives me the integral of e to the u du multiplied by 1/2. Integrating with respect to u, finding the antiderivative function, gives me 1/2 e to the u plus the constant of integration. Then I back substitute to return to the original independent variable, and I get 1/2 e to the x squared plus the constant of integration. Now let's look at example 7. There are lots of examples in this video because it is such an important concept, and you really need to see them all. The more practice you have, the better at it you'll be. Like I said, this is my #1 skill that you come out of Calculus 1 knowing. Let's look at the indefinite integral of the quantity square root of x added to 1, all raised to the 4th power, divided by 2 times the square root of x dx. In this case, I can see that I do have composition. I have the quantity square root of x added to 1 raised to the 4th power. The question is, do I have the derivative of the inside function square root of x added to 1? Well, the derivative of a square root is 1 over 2 the square root. So in fact, it is there. It looks like division, but I could rewrite this so that it looked like multiplication. In other words, I could write this as 1 over 2 square root of x times the square root of x added to 1 to the 4th power dx. Again, my inside function, which is g of x, is going to be the base of the thing raised to the 4th power. And my outside function is going to be that 4th power. Then I set u to be equal to the inside function, square root of x plus 1, and I take the derivative. When I take the derivative with respect to x, I get 1 over 2 square root of x. This is the derivative of u with respect to the original differential, which was dx. WRT stands for with respect to. Then I abuse the notation and swing the dx around and solve for du. Finally, I go ahead and substitute in place of u and in place of the remaining factors. In this case, you can do it a couple ways. The last time I isolated the remaining factors, so this time I'm going to solve for dx. To solve for dx, I have to multiply both sides by 2 square root of x and then times du. When I substitute, I'm going to have the following. I replace the inside function with u, and I'm going to replace the 1 over 2 the square root of x dx. Well, actually just the dx. In this case, I get the integral of u to the 4th divided by 2 square root of x times dx, which is 2 square root of x du. The 2 square roots of x cancel, and I get the integral of u to the 4th du. This is simply going to be an application of the power rule for integrals. When I apply the power rule, I add 1 to the power and divide by the new power. Then I add the constant of integration. This gives me u to the 5th divided by 5 plus c. It's an indefinite integral, so I must return to the original, and I'm going to write it as 1/5 times the quantity root x plus 1, all raised to the 5th power, plus the constant of integration. Do not forget to return to the original independent variable or to add the constant of integration. I've been known to take off 20 to 30% a piece for such errors. Let's now look at example 8 and example 9. Example 8 is an exponential function. It's actually the hyperbolic tangent function, which it's not trig at all. It's called hyperbolic trig because the derivatives and integrals follow the pattern of the trig functions. But it's actually an exponential function, as you can see by the definition here. There's no obvious place to find a u. There's nothing being raised in parentheses to a power outside, and there's no one thing in the power. I do have negative x inside of a couple exponentials, but I've got others as well. And they're being added and subtracted to other terms, not simply multiplied. In a case like this, where there's no obvious choice of u, but it is written in fraction form, try taking the denominator to be u. In this case, what we're going to do is we're going to let the denominator be u. If the denominator e to the x plus e to the negative x is u, then when we take the derivative with respect to x, we get e to the x minus e to the minus x. Notice that this is actually the factor that I have in the numerator. In parentheses, the entire quantity, e to the x minus e to the minus x. Now I can abuse the notation and swing the dx around to the opposite side. This time, we're doing u-substitution, but we didn't actually see the composition. I'll show you where the composition is once we complete it. In this case, we then have exactly the remaining factors inside of our fraction. And so we can immediately substitute. Again, we are substituting for the denominator to be u. Since the denominator is u and the remaining factors give us du, we have du divided by u. That's correct. The original composition, which we probably did not recognize, was 1 over u. In other words, it was a fraction. And the inside function was the e to the x plus e to the minus x. The outside function was the rational function 1 divided by x. But again, this is not something that you might recognize. However, when in doubt and you can't think of anything else to do to integrate, try setting the denominator to be u. Now, this is the one polynomial type equation. Actually, it's not a polynomial because of the negative exponent, but it is the one type that we cannot apply the power rule to. You must memorize that the integral of 1 over u du is the natural log of the absolute value of u. And again, those absolute values are not optional. They're mandatory. Once you've rewritten it as the natural log of the absolute value of u plus a constant, replace the u with your original definition, e to the x plus e to the minus x, inside the absolute values. Don't forget, you must return to the original variable when you have an indefinite integral, and that you must have the constant. In the next one, we have cosine of t divided by sine squared of t dt. I do have composition. Remember that you can rewrite this as the integral of cosine of t divided by the quantity sine t being squared dt. In fact, it will be easier on this one if you go one step further and move the denominator factor to the numerator by changing the sign of the exponent to write it as cosine t times quantity sine t raised to the negative 2 power dt. Now we can see more clearly that the inside function must be sine of t, and the outside function is t to the negative 2. The derivative of the inside is cosine of t, which does appear as a factor. Now that I've gotten it started for you, pause the video, work it out, then turn the video back on so we can check your answer. So let's compare our work. We decided that sine of t was the inside function, so taking the derivative with respect to the differential dt gives us cosine of t. Then we abuse the notation by swinging the differential dt to the opposite side. Since cosine of t dt are the remaining factors inside the integrand outside of the composition, I chose to just leave it that way. You can also solve for dt and substitute. When I substitute, I replace the sine of t with u, and the cosine t dt gets replaced with du. This gives me u to the negative 2 du. I can do this one with the power rule for integrals. I add 1 to the power negative 2 and divide by the new power, which gives me u to the negative 1 divided by negative 1, which converts to 1 negative 1 over u plus the constant of integration. Finally, I back substitute to end up with negative 1 sine of t plus the constant of integration. We're now ready to turn our attention to the definite integral. I spent a lot of time on the indefinite integral because that is a part as well of the definite integral. The only piece it's missing is substituting in the limits of integration. We will see that these are, in that sense, rather different from the antiderivative function. However, they also have a lot of similarities. And again, there's more than one way to proceed. There is one way that leads to fewer mistakes and is shorter, but for some reason, students seem to prefer the longer, more fraught method. Let's see what they are now. How is this abuse of notation and this substitution for the inside function going to be handled with a definite integral? Well, the basic difference are the limits of integration. When we convert to a function of u, we can also convert the limits of integration from, say, x values to u values. Then, when we complete the integration on u, we can substitute the u values in and get the answer without ever returning to the original variable. The other option is not to convert the limits of integration, but to keep them x values. You still are going to substitute with u and du, which means when you integrate, it will be in terms of u. But if the limits of integration are still x values, you'll have to back substitute to the original variable x before you can substitute in those limits of integration. This is the longer method, and it does lead to more careless mistakes. I'll show you both, and then you can choose the one that you think is best for you. Here's the theorem for u-substitution with definite integrals. We have basically the same conditions. Let u be some function g of x, which is going to be inside of another function. Let its derivative, g prime, be continuous over some interval, say from a to b. Let the outside function f be continuous at the corresponding range of g. Then we can say that the definite integral from a to b of f of g of x multiplied by g prime of x dx is the integral from g of a to g of b of f of u du. In other words, we are substituting the value x equal a into our definition for u to get a u value instead. And we substitute the x value of b into our definition of u to get a u value for that limit of integration. Then everything is in terms of u, and we can evaluate and find the net area without ever having to go back to the original variable. Let's look at an example with both methods worked side by side. I am hoping to convince you to use method 2. Let's do method 1 first. This, for some reason, seems to be the method that gets taught the most often in high schools. We have the definite integral from 0 to 2 of 2x divided by x squared plus 1, all raised to the second power, with differential dx. We can see that we have a composed function of x squared plus 1 on the inside and the second power on the outside. In fact, we can do what we did previously. We can move that term to the numerator if we want to. In this case, I check to see if I have a multiple of the derivative of the inside in the integrand as a factor. The derivative of x squared plus 1 is 2x, and I do have a 2x as a factor in the original integral. For method 1, we're not going to replace the limits of integration, x equals 0 and x equal 2. Instead, we'll substitute for u and du. We'll integrate with respect to u, then back substitute to the original variable x. Let's take a look at what that would look like. In this case, we know that du is 2x dx. So we replace the 2x dx with du. We knew the inside function is x squared plus 1, which we replace with u. This gives us 1 over u squared du for the integrand. I'm not changing the limits of integration, but they no longer match the variable inside the integrand. Because they don't match, it is mandatory that you write x equals 0 and x equal 2. You need to distinguish so you don't forget and think they're u values. Once we have this, we go ahead and integrate with respect to u. In this case, in order to integrate this, I'm going to rewrite it as u to the negative 2 power du. Once I have this, I know I can use the power rule for integrals. This gives me u to the negative 1 divided by negative 1, which I rewrite as negative 1 divided by u. I cannot substitute the limits of integration. Variable, and the antiderivative is u. The limits of integration are x values. I must back substitute and get out of u and back to x before I can substitute. Because I had a negative 1 in the antiderivative, I chose to take care of it by reversing the limits of integration and making them go from 0 to 2 to 2 to 0. Then I back substitute for u as x squared plus 1. Now I can drop the x equal on the limits of integration because the antiderivative is written in terms of the original variable x. Substituting in the upper limit of integration and lower limit of integration and subtracting gives me finally the value of 4/5. This is the area, the net area, under the original integrand function between it and the x-axis. Now, you can tell by comparing to the right that it is in fact longer. Let's go back and see what it would look like in order to do it without returning to the original variable x. This is method 2, which is my preferred method for you to use. I'll be honest, I do and have used both methods extensively. But over time, I've come to see that method 2 is actually much better. For method 2, again, we know u is x squared plus 1 and du is 2x dx, taking the derivative and abusing the notation. And I know that I want to stay in u and not go back to x. So I'm going to find u limits to replace the x limits. The original integral started at x equals 0, but I have an equation which defines the relationship between u and x, and it's even solved for u. So I replace the variable x with 0 to get 0 squared plus 1, which is 1. I'm going to replace the lower limit of integration x equals 0 with the limit of integration u equals 1. For the upper limit of integration, which was x equal 2, I instead get 5. When I substitute, this means that instead of x equal 2 for the upper limit of integration, I get u equal to 5. Now I substitute the new values into the original integrand. This changes the limits of integration from 0 to 2, which are x values, to 1 to 5, and their u values. It's not necessary to write u equal because they match the variable inside the integral. Once I have this, I go ahead and integrate with respect to u exactly as I did in method 1, by writing it as u to the negative 2, integrating and reversing the limits of integration to take care of the negative. And I substitute the upper and lower limits of integration, and I get, again, 4/5 square units of area. Let's take a look at our function 2x divided by, and I've got the wrong one up, divided by x squared plus 1 quantity squared between 0 and 2. It's a neat little function, kind of sloping down and up to the x-axis on both sides. It's kind of a neat little function that you can see there, defined for all reals. Let's now move on to example 11. In example 11, we again can see that we have composition with 2y squared minus 3 on the inside and y to the 5th on the outside. The derivative of 2y squared minus 3 is 4y. I need a multiple of y as a factor in the integrand, and I have y as a factor in the integrand. Choose your method now, either method 1 or method 2. Pause the video and work it out, then turn it back on so we can compare our results. In this case, we have the original variable of y, which is a little unusual, but it still works the same. Remember that when you're dealing with a definite integral, the variable used is actually a dummy variable, since the result is going to be a finite real number. It doesn't matter what we use. We're getting net area. The inside function is 2y squared minus 3, and the outside function is y to the 5th. The derivative of u with respect to y gives us 4y. Next, we abuse the notation by swinging the dy around to the opposite side. This gives us du equal to 4y dy. In this problem, I chose to go ahead and solve for the original differential dy to get du divided by 4y. Now you have to choose whether you're using method 1 or method 2. I've worked both this time, though I won't the next time, just so you can see how they play out. I think with method 2, the calculations become, well, a little easier. When I look at method 1, I go ahead and make the substitution for u and for dy. I know that because I've switched from dy to du, that I have to put labels on my limits of integration. Y equal -1 to y equals 0. The y's cancel, and I get 1/4 of the definite integral u to the 5th du, but from y equal -1 to y equals 0, which doesn't match the variable in the integral. I integrate using the power rule to get 1/24 u to the 6th. But because I didn't change the limits of integration, I've got to go back to the original function. U gets replaced by what it was equal to. Now I have everything written in the antiderivative in terms of y, so I can drop the labels on the limits of integration. I substitute the upper and lower limits, do quite a bit of arithmetic. You should end up with 90⅓ squared units. When you're looking at method 2, instead, you need to change the limits of integration to u values. You take the definition of u as 2y squared minus 3. You substitute the lower limit of integration in place of the variable y. That gives you that u is -1. Then, to replace the upper limit of integration, y equals 0, you replace the y with 0 to get the upper limit of integration -3. Don't worry about the fact that these appear to be going backwards. It'll take care of itself. Then you go ahead and substitute them in, and you integrate with respect to u. Again, you end up with 1/24 u to the 6th, but this time evaluated between u equal -1 and u equal -3. You substitute the values in, the arithmetic is simpler, and you get 90⅓ squared units. This is kind of an interesting little function. I really kind of like it. It's got some nice, well, changes in curvature and maximums and minimums to it. And we're looking at the area here between -1 and 0. And you can tell that it is, in this case, all positive, strictly above. This must be 91/3 square units. Notice that I had to change the scale to get the detail to show up. Let's take a look now at example 12. Example 12 is x squared cosine of pi over 2x cubed with respect to x from x equals 0 to x equal 1. In this case, the inside function is the argument to the trig function. And it's a constant pi over 2 times x cubed. The derivative of it would be 3 pi over 2x squared. I have a multiple of that, x squared, as another factor in the integrand. Pause the video to work this one out, and then we'll compare our results. Let's now see how you did. Our inside function is pi over 2x cubed. Our outside function is cosine of x. When we evaluate, we take the derivative of u with respect to the original differential dx, and this gives us 3 pi over 2x squared. We abuse the notation and swing the dx around. I chose to isolate the remaining factors inside the integrand other than the composed factor. This gave me x squared dx equal to the reciprocal of 3 pi over 2, which is 2 over 3 pi times du. Now, I know that you have a choice, but I'm trying to push you towards method 2. I'm going to use method 2 to solve the rest of this problem. That means that I need to change my limits of integration. I'm using the definition of u as pi over 2x cubed. When x is 0, u becomes 0. And when x is 1, u becomes the pi over 2. And I substitute out the limits of integration, u for the inside function, and the remaining factors for 2 over 3 pi du. When I'm done, I can take the 2 over 3 pi and pull it to the front of the definite integral as a constant. Then this gives me the definite integral from 0 to pi over 2 of cosine of u du, which will give me sine of u. Next, I leave the 2 over 3 pi outside as a factor, and I find the difference when I substitute the limits of integration into the antiderivative function. Notice that my substitution here is relatively simple and straightforward. In method 1, it would not be. This gives me 2 over 3 pi square units of area. This is also a kind of fascinating function. When you look at it, you can tell that it begins oscillating so incredibly rapidly out here on the edges. The Desmos just can't handle it, and it resorts to just kind of painting it all red. In fact, it is still a function. Here, near the origin, the oscillations are not so tight together, and we can see the part that we're interested in between 0 and 1. This tiny amount of area here is equal to what we got, which I believe was, well, what was it? It turned out to be 2 over 3 pi square units. What we want to do now is we want to take a look at 2 last examples. These come up so frequently in Calculus 2 that it's good for you to have at least had a little bit of experience with them before you get there. This is what happens when you have a power of a trig function, like sine squared of x or cosine squared of x. You may remember the reduction formulas from trigonometry, and that sine squared of x is half of the quantity 1 minus cosine of double the angle, and cosine squared is half of the quantity 1 plus cosine of 2x. The way to keep the 2 formulas distinct is to remember that sine is origin symmetric. Replacing negative x for x will give you the opposite of the function. So I associate it with a negative. It's odd symmetric. Cosine is an even function, which I associate with the plus sign, and that gives me the plus in the middle. Whatever works for you, these are two formulas that you need to have memorized. They don't come up all the time. They come up frequently enough that you just don't have time to go look them up every time you need them. Let's see how we can use these formulas to integrate and why they're in this section on u-substitution. We'll start with example number 13. When we look at example 13, we can see that we have the indefinite integral of sine squared of x dx. Should end up with an antiderivative function in terms of x plus the constant of integration. However, we cannot directly integrate sine squared of x. Use the reduction formula to rewrite the integrand instead as the integral of 1/2 times 1 minus the cosine of 2x with respect to x. This is actually two terms written in a combined form. It'll probably be easier for you if you go ahead and distribute it out so that you have 1/2 minus 1/2 the cosine of 2x with the differential dx. You know that you can find the integral of a difference by taking the difference of the integrals. In other words, I can simply rewrite this as the integral of 1/2 dx minus the integral of 1/2 cosine of 2x dx. And now you should see why it's in this section on u-substitution. Second term leads to a composed function with 2x on the inside and cosine on the outside. Let's go ahead and complete this problem now. To integrate the first one, I simply apply the power rule in reverse, thinking of this as 1/2 x to the 0 to get 1/2 x to the first. And the second one, I have to do a u-substitution. What we typically do when we're doing a u-substitution is we come over to the side and we write u equals, in this case, 2x. And then we go ahead and take the derivative of both sides. It's not uncommon to take the derivative and abuse the notation at the same time, getting du equals 2 dx. Now that I have this, I need to make my substitutions into the equation. But I don't have a 2 dx, so I'm going to solve for dx. This gives me dx is du divided by 2. Now, when I complete this, the first term is just hanging out, waiting for the second to be done. And the second becomes the cosine of u times du divided by 2. The second 1/2 can be factored out and multiplied by the 1/2 already there to give me 1/4. This gives me 1/2 x from the first term minus 1/4 the integral of cosine of u du, which integrates to sine of u. Finally, we get 1/2 x minus 1/4 sine of u plus c. Next, we need to back substitute to get back to the original independent variable. We replace our u with 2x. Now, you may be wondering why, since we had sine of x being squared, that we didn't do a u-substitution with sine x, the inside function, and x squared, the outside function. The reason is pretty straightforward. In order to integrate directly using u-substitution, you have to have a multiple of the derivative of the inside function. Sine x is our inside function, have to have a multiple of cosine x inside the integrand, and we do not. That means that I cannot do u-substitution with sine of x as u. Instead, I must use the reduction formula. We have one last one to work with, is going to be with cosine squared. And this one is a definite integral. I've already worked it out for you to save a little bit of time. So let's take a look at what I have. Again, even if you wanted to, you cannot do u-substitution directly, even though we do have the cosine of 8x being squared. Problem is, we don't have a multiple of the derivative of the inside function. The derivative of cosine of 8x would be negative 8 sine of 8x. We could deal with the loss of the negative or the 8, but we have to have a multiple of sine of 8x, and we do not have that in the original integrand. So what we have to do is use the reduction formula. In this case, the argument to the trig function is 8x. So when we apply the reduction formula, we get 1/2 times the quantity 1 plus cosine, double the original angle, so 8x becomes 16x. With respect to x, evaluated between x equals 0 and pi over 4. Next, we split this into two separate integrals. The first term can be integrated directly. We don't need to do anything special to that part. The second one, however, is going to have now some kind of u-substitution. We have cosine on the outside and 16x on the inside. The derivative of 16x is 16, which is just a constant. So we can definitely do u-substitution on the second term. We set u to be the argument to the trig function, take the derivative with respect to the original differential dx, and abuse the notation by swinging the dx around. Notice that I'm now doing it in one step. This gives me du equals 16 dx. Because I don't have a 16 as a factor in the integrand, I solve for the differential dx to get du over 16. Now I need to replace the limits of integration, switching from an x integral to a u integral. When x is 0, u is 16 times 0, which is 0. And when x is pi over 4, u is 16 times pi divided by 4, which gives me 4 pi. When I substitute, I get the integral from 0 to 4 pi of cosine of u times du over 16 with the 1/2 from the reduction formula on the outside. Next, we go ahead and evaluate the two integrals. In the first term, we go ahead and substitute the limits of integration to get pi divided by 8. When we integrate cosine of u with respect to u, we get sine of u. Notice the 1/16 and 1/2 combine to give 1 over 32. Next, I substitute the limits of integration, but because they're both multiples of 2 pi, they both become 0, which means that the amount of area that I've got underneath this curve is pi divided by 8 square units. Let's take a look at the graph and see what it looks like. When we look at the graph, we can see our graph of cosine squared of 8x, and we have marked off the section between 0 and 4 pi. We've shaded the area between the curve and the independent axis. This is what we got with pi divided by 8 square units. This is how we deal with a power of sine or cosine. There are many other methods that we'll have to learn in Calculus 2 to deal with other combinations of sines, of powers of sine and cosine. I know it's been a little bit of a longer section, but u-substitution is just too important not to really hammer it home. In our next video, we'll be taking a look at how we integrate with exponential and logarithmic functions. You already know the antiderivatives, so it should be pretty straightforward to apply what we've learned about u-substitution, but with exponentials and with integrals that give rise to natural log. I'll see you for the next video.